In this section, we're going to do the conic section called a hyperbola. And I wanted to point out right off the bat that hyperbolas have a lot of similarities to ellipses in their basic structure, but where you're going to draw the curve is going to be entirely different, and there are some differences in the formulas as well. If you can look at the picture and ignore the green for a minute, this is the same picture that we drew when we had an ellipse. And you'll notice there's a blue ellipse in there. And the blue ellipse is connected by those 4 purple points. Well, the 4 purple points came from the A value and the B value that we counted away from the center. And the center was right in the middle of those 4 dots. And so we drew the ellipse as a curve through those 4 dots. What we're going to do now with hyperbolas is we're going to use those same 4 dots, and they're going to be counted using A and B from the center, but instead of drawing an ellipse through them, we're going to draw this box through them. And that box will not connect the 4 points like in a diamond shape, but what it will do is it'll connect those 4, or it'll be drawn through those 4 points with horizontal and vertical lines, and it will create this rectangle that I have drawn in green. The rectangle is important because it creates what we call the asymptotes of the hyperbola. And the asymptotes are going to act as guidelines to show you how wide you should draw your hyperbola. And so you draw diagonals through the box. So you draw 2 diagonals through the box and beyond the box. You make them unending lines. And I always make them dotted lines. And those are representing, so those green dotted lines are the asymptotes, and they're just diagonals of the rectangle. So that's the only reason we need the rectangle, is so that we can draw those diagonals, which acts as our asymptotes. Once you have that drawn, then you need to figure out which direction your hyperbola is going. And you determine the direction of the hyperbola not by where the longer axis is, but you do determine it by what letter comes first. And so let's look at our 2 formulas. I did want to point out that in this first hyperbola formula or equation, that it looks very similar to our ellipse equation. The difference is there's a minus sign instead of a plus sign. That also, I wanted to point out something else that immediately occurs because of that. If this is a minus sign, then that will also affect our c² formula. And you'll remember in an ellipse, it was a² minus b², but in a hyperbola, it's going to be a² plus b². So not only does the sign change in the equation itself from plus to minus, but the c² equation also changes from minus to plus. Just remember, when you're trying to mix them all together, that the c² formula and the equation formula will always have a different sign. They'll always be opposites of each other. So in ellipse, it was plus and minus. In the hyperbola, it's minus and plus. So that should help you keep those straight. So that's another way that it is very similar to the ellipse, but has a kind of an opposite effect. Now, the other big difference between a hyperbola and ellipse is that A is not always bigger now. A is not going to be the bigger number. A is going to be the first number. And so it's going to be, a² is going to be in the first spot every time. So they're not labeled A and B, but you just got to know in a hyperbola, it's not the bigger number, it's the first number on the bottom. So the way you'll know which direction to draw the hyperbola will not be determined so much by the A, it will be determined by whatever comes first. So notice the difference. Instead of switching the a² and the b² spots like we did with the 2 different kind of ellipses, we're switching the x and the y spots. And that will determine, whichever one is first, will determine which direction you draw the hyperbola. And so in the blue one, I'll draw this one in blue, you would use this as your vertex and your other vertex, and you would draw your hyperbola coming out of those, because an x first hyperbola means you're going to graph it side to side in the x-axis direction. And so that is called a horizontal hyperbola. It's going side to side in the direction that the x's go. X's go side to side as well, and it's because x is first. Then in red, I'm going to graph what it would look like in this one. It's the same box that was created. So let's say it's the exact same numbers that created the same box, but in this case the y was first, and so we're going to take the box and let these be the vertices now, and our hyperbola will come out this way. And notice I make it really wide because I'm trying to hug those asymptotes in both cases. In the blue or in the red, I'm trying to get closer and closer to those asymptotes without ever crossing over them. And you'll never have these two pictures in one picture. You'll either have the blue version or you'll have the red version, depending on if X or Y are given first. But the A and the B don't change places. They stay A first, B second. And the formula in both the up and down kind of hyperbola and the sideways kind of hyperbola stays c squared equals a squared plus b squared in all hyperbolas, whether it's an up and down kind or a side to side kind. And remember, the purpose of the C is for focus. C always has to do with the focus in all our different kind of conic sections. And so once you find the value of C, that's the distance between the center and the focus. And so it will be, in the red picture, it'll be here and here, because it'll be a little further away than the vertex. So the focus, remember, is always inside the curve. It's never outside the curve. So it's kind of like where it landed with a parabola. It's kind of inside the curve, close to the vertex. And then the blue one will have its foci, you know, somewhere around here and somewhere around here. Those will be the foci for the blue hyperbola. And so these little red points that I had here were left over from the ellipse. It's inside the ellipse. Those have nothing to do with the hyperbola. That was just left over from my picture that I copied from the first page of the ellipses. But the foci will be in the red and the blue spots as I have drawn. The vertices of the hyperbola are here in the blue one, vertices, vertex and vertex, and in the red the vertices are here and here. The vertices always have to be attached to the curve, and so if the curve is going up and down, the vertices are up and down. There are no co-vertices. The co-vertices per se from the ellipse actually just helped us create the green box, but they're not called co-vertices because vertices always have to touch the curve, and co-vertices also have to touch the curve. Anything with the name vertex, it actually is part of the curve, and so we don't call those things that are not part of the hyperbola co-vertices, but they were important points to help us to draw the box, which helped us with the asymptotes. Sometimes they'll ask you for those equations of the asymptotes, and it's really not that hard when you think of y equals mx plus b. In this case, the m will be positive on that line, and the m will end up being negative on this line because it has a negative slope. And where that you'll get that m is just the rise and the run from this point, the center, out to one of the corners of your box. If you just count the rise and count the run, that will determine your m. And since these are centered at 0, 0, or the y-intercept is 0, you won't have a b. Eventually, once you move this hyperbola off the center, your b will be wherever it crosses the y-axis. But for now, we'll focus on asymptotes that don't have a b or have a b of 0, and you'll just count the rise and the run to get your m. The last two pieces of information about a hyperbola you need to know is that there's nothing called the major axis and the minor axis, because A is always associated with the distance between the center and the vertex, and A is sometimes shorter and A is sometimes longer. So on the red hyperbola piece, the A is actually shorter and the B is longer. That would be for the red hyperbola. But for the blue hyperbola, A is still going to be called the distance between the center and the vertex, and it's longer, and B just helps us get to the edge of the box, and it is a shorter piece. So A is sometimes longer and A is sometimes shorter. It just depends. But what you need to know about the conjugate axis and the transverse axis is the transverse axis is your main axis. That is the one that connects the vertices. So on the red hyperbola, this would be the transverse axis. It connects the two vertices, and that distance will be 2 times A. Then the other axis that isn't really part of the hyperbola, so we're talking about the red hyperbola, not the blue one, this longer axis here would be called the conjugate axis. It does not connect the vertices of the red hyperbola, but it is important in creating the box. So it's still called an axis, but it's called the conjugate axis, and it does not connect to the hyperbola at all. So the main axis that connects the vertices is the transverse axis. The not main axis that does not connect the vertices is called the conjugate axis. And so sometimes one is longer than the other and sometimes one is shorter than the other, but the transverse axis will be a length of 2A and the conjugate axis will be a length of 2B. Now let's do an example given an equation and we're supposed to find the key points and graph the hyperbola. First of all, you know this is a hyperbola because you see the minus in it. And you know that this is a hyperbola that's going to go up and down because the y is first. So we know we're looking at a hyperbola that is in this direction. Also, you want to remember that these two letters represent A and B, but it's not the bigger one that represents the A, it's the first one that represents the A. And so A is going to be 3 because A squared is 9, and B is going to be 4 because B squared is 16. So therefore, remember that the A does not always have to be bigger than the B. It might be sometimes, it might not be sometimes. But it does always happen first. So once you have your A and B, you can draw your 4 points. Notice A has to go in the direction of the y because the A squared is under the y squared, and the B has to go in the direction of the x because the B squared is under the x squared. And rather than drawing an ellipse through those 4 points, you draw a box through those 4 points, and then you draw asymptotes going through the diagonals of the box, and then your hyperbola is going to be drawn close to those asymptotes going up and down. And I'll put the rest of the information here so that you can process how you would find the foci. So here's the completed hyperbola with the foci in the proper place. Notice that the C ended up being 5, and so we counted 5 from the center to get our foci. And then also we have the length of the transverse axis and the length of the conjugate axis, and the transverse axis has to connect the vertices that are part of the hyperbola, and that is a length of 6. It's 2 times A. And then we have the conjugate axis is a horizontal line that connects those two other dots that we don't really call covertices, but they connect those two, and it's going in a sideways direction, and it is basically 2 times B, which is given there. So that is the hyperbola that matches this equation.